So in the previous lecture, I introduced to you reaction rates and the rate law. And there is the expression for the rate law that relates reaction concentration to reaction rate. The rate law must be determined by experiment. Before we start today's lecture, I'd like you to have a go at this question as a recap of the previous kinetics lecture. So pause the video and have a go at using this data to determine the rate law. There are 3 experiments here that you can use to determine the rate law and to calculate the rate constant. I trust that you have now paused the video, had a go at this question and started the video again. So to determine the rate law, we need to look at the different experiments where the initial concentration of these 2 reactants have changed for each of the experiments. Between the first and the second experiment, the concentration of the second reactant has doubled, and you can see that the rate has doubled. If you look at the difference between the first and the third reaction, the second and the third reaction experiment, you can see that the concentration of the first reactant has doubled, the second reactant has stayed the same, and you can see that the rate has also doubled. So this allows you to see that the rate is proportional to both of these reactants. So the rate law is the rate equals K times the concentration of both of the reactants. So that's what you should have got for that part of the question. The second part of the question is to take one of these experiments, plug those numbers into the rate law to calculate K. And if you did that correctly, you would have got that K equals 2.7 times 10 to the minus 4, molar to the minus 1, second to the minus 1. Remember, this is a second order reaction, and that different order reactions will have different units for the rate constant. Lecture 2 is in 2 recordings. So we have lecture 2 part A and lecture 2 part B. At the end of this lecture part A, you will be able to explain what first order reaction is and have a good understanding of how to use equations that are associated with first order kinetics. You'll be able to draw graphs from data of concentration versus time, and you'll be able to calculate the rate constant from first order reaction graphs and be able to calculate half-life. So reaction order tells us how the reactant concentration influences the reaction rate. We're going to learn in later lectures how this can tell us something about the mechanism of the reaction. The rate constant, which we determine from the rate law, will have units that depend on the overall order of the reaction. Now, I've mentioned this before, and I'll just show you how that occurs here. So a first order kinetics reaction will be rate equals K, the rate constant, times the concentration of one of the reactants, but to the power of 1, because it's a first order reaction. The units of rate are molar seconds to the minus 1, and the units of concentration are molar. So that means that the units for the rate constant here will be seconds to the minus 1, and this means we have the same units on both sides of this equation. If we have a second order kinetics reaction, then we'll have the rate equals K times reactants, but this time to the power of 2. The N plus M, if there are 2 reactants, would equal 2. So the overall order of this reaction is 2. The units of rate are molar per second, and the units from concentration are now molar squared. And so to have the units balanced on both sides of this equation, the units for the rate constant will now be molar to the -1, seconds to the -1. Now in nature, a number of different types of reactions will have first order kinetics. We will see this in the radioactive decay, which is exponential. And by being exponential, that means it is first order, as you will see in the next slides. In biology, growth rates are often exponential, and therefore they are first order. And in pharmaceutical science, drug decomposition on storage is often first order, and again you see that by an exponential reduction in the concentration of the drug against time. So let's think about this from the point of view of first order reactions in more detail. So for the reaction A going to products, the kinetics are first order for A if the rate equals K times the concentration of A to the power of 1. So the rate, as we know from our rate expressions, is measured by minus dA by dt in that reaction. So minus dA by dt minus the rate of the rate that the reactant A is consumed is equal to K times A if it's a first order reaction. That expression there can be integrated. And if you integrate that expression, you will get an equation that looks like this. By integrating that expression, you'll get an equation where you have log of the concentration of A at time t. Log here is ln because it is natural log. Okay, equals minus kt plus the natural log of the concentration of A at time 0 at the beginning of the reaction. So that step of integrating the rate law, I can go through with some of you at a separate time, but you do not need to know how to get from the rate expression at the top there to the integrated first order rate law. But you do need to think about this new equation that we have. This equation allows us to link concentration at any time in the reaction to the rate constant. The equation shows how concentration of A depends on time. And the equation is in the form of a y equals mx plus c equation, which can be very useful. So this equation allows us to measure the concentration of our reactant with time, so at different time points as the reaction proceeds, and then to plot that, and from that we will be able to determine what the initial concentration was, if we didn't already know that, and we would be able to determine minus K. In other words, we'd be able to determine the rate constant. So if you look at this equation in the form of y equals mx plus c, y, what you need to plot on your y-axis, will be the natural log of the concentration that you measure. And x would be time. And this means that minus k, so minus the rate constant, would be m, which is the gradient, and the y-axis intercept would be natural log of the concentration at the beginning of the reaction, which of course is a constant. So the integrated rate law for first order reactions can also be expressed in terms of a ratio. So what we have in that expression there is the natural log of A at time t equals minus kt plus the natural log of the initial concentration of A. If we get it so that all of our concentration terms are on the same side of the equation, we will have that the natural log of AT minus the natural log of A naught equals minus KT. Now our log rules that you may know from your maths classes mean that if we take away two logs, we actually have a ratio there. That is the same as the natural log of AT over A naught. So that means we have an expression for our integrated rate law that uses the ratio AT over A naught rather than the individual values of AT and A naught. And that can be a useful form of the expression that you will see in later lectures. So here we have the natural log of AT over A naught equals minus KT. If we plot the concentration of a reactant against time for a first order reaction, we will see an exponential decay. And this is the shape we often see when looking at the decomposition of a drug. If we use the integrated rate law for a first order reaction, we can also see this relationship. And this can now be expressed as a straight line graph, because we have it in the format of y equals mx plus c. So this means if we now plot the log of concentration against time, we will get a straight line. From this straight line, we can now calculate the value of the rate constant k from the gradient. The gradient of this first order reaction, log of concentration against time, is equal to minus k. Now you're always going to remember that it's minus k even if you didn't know the equation, because you can see it's a negative gradient there and our rate constant wouldn't be negative. So here's a question for you. Given the concentration and rate data for reaction, what graph would you plot to show that the reaction is first order with respect to A? And from the previous slide, I'm sure you can give us that answer. And how would you determine the value of K from this graph? And what would be the units of K? And an exam question might also finish with this question. A first order reaction is 25% complete after 280 seconds. Calculate the rate constant. I want you to think about what form of the first order reaction equations that you have seen would you need to use to be able to calculate the rate constant with that information. Pause the video and write down the answers to these questions the best that you can. So I hope you've now paused and tried these questions. The first part you'll be able to get from the previous slides fairly quickly. So if you've got a concentration and you've got rate data for a reaction, the graph that you can plot that would show if the reaction is first order would be log of concentration against time. And we get that because we know that the integrated first order rate equation, if you plot the log of concentration against time, you would get a straight line. So this will only be a straight line if it is a first order reaction. And then once you have that, you would be able to get the gradient from that straight line graph, and the gradient would equal minus k, so minus the rate constant. The third part of the question was a first order reaction is 25% complete after 280 seconds, and to calculate the rate constant. And here you need to recognize to use the integrated first order rate equation in the form that has the ratio of concentrations, because you're not given exact concentrations here, you're given a percentage of completion. So you use the equation log of the concentration at the time of the reaction, which in this case is at 280 seconds, over the initial concentration, and that equals minus kT. And if the rate is 25% complete, there is 75% of reactant remaining. So the ratio of the concentration over the initial concentration is 75 over 100. So it's 0.75. So you don't need to know the absolute values of concentration here, just the ratio between those two numbers. So if we use this equation, that would mean the natural log of 0.75 equals minus k times the time, which is 280. So, and if we rearrange that and we use our calculators, we can get that the rate constant equals 1.03 times 10 to the minus 3 seconds to the minus 1. And if you got that last part right, then very, very well done to you. But if you didn't, don't worry, that's the first time we've been through an example exactly like that. We know that first order kinetics show exponential reduction in reactants during the reaction. So we see an exponential decay, and that defines it as first order. And this means that there will be a constant half-life for work that you may have done in the past looking at the rate of decay of a radioactive material. You'll understand that concept, that the half-life is the time taken for 50%, in this case 50% of the reactant to be consumed. And that will be constant. It doesn't matter what the starting concentration is, the half-life will always be the same. If we look at the integrated first order rate equation, we can see that the half-life is the point where the concentration that we measure is half the initial concentration. So we can say that AT equals a half of A naught. And then we can substitute either the A naught value or the AT value into that top equation there. And we can simplify the equation. And if we do this, we end up with an equation that says the half-life equals the natural log of 2, which is 0.693 over K. So you can see that the half-life is constant, and we can determine the half-life if we know the rate constant. So try that out for yourself to make sure you understand that process. Here's a question for you to try for a first order reaction where K equals 0.03 1.03 times 10 to the minus 3 seconds to the minus 1. What is the half-life? And again, pause the presentation and have a go at that question. To answer this, you would do the half-life equals 0.693 over K, because this is a first order reaction. So that would give you 673 seconds. So if you got that right, then very, very well done to you. So I'd like us to take a break here, and we'll come back in the next video. So you'll need to go to the next video, which will be entitled Second Order Reactions. So take a break at this point.